Alright, so in this problem we are studying a house with a roof and it has dimensions shown in the drawing. We want to find the magnitude and direction of the net force that the atmosphere applies on this roof when the outside pressure drops suddenly by 75 millimeters of mercury before the air pressure in the attic can adjust. We want to write our answer in Newton. Now, if we look here, first of all, we are considering the force. Let's talk a little bit about the force exerted by atmospheric pressure. So we know that the force exerted due to a pressure is equal to P times the area. So the pressure times the area. And we know that this force is perpendicular to the surface area. Here we have two surfaces. So our first surface is over here, and this is the force that will be exerted on it. Our second surface is here, and this is the force that will be exerted as well. So we can name these F1 and F2, let's say, for the force exerted on each surface. Now, I have drawn these forces to be outwards because the pressure drops. So the air pressure inside has become more than the air pressure outside. And then the force is going to point outside this surface. Now, we said this force is equal to the pressure times the area. Okay, we know how much the pressure drops, and then we can know how much the force is going to change. Speaking of the area, we saw that we have two surfaces, each of an area equal to length times width. The two surfaces are rectangular, so we can find the value of this area. We can also now talk about the components of the forces a little bit because we are interested in the net force and we have two forces here. So if we want to talk about the net force of these two forces, first of all, let's check a figure, let's say a front view of our house, because maybe this will help us more in checking out the forces and their net values. So we said this is F1 and this is F2. Now, let's draw these two forces from the same point because this is very helpful in finding the net force. So again, this is F1, this is F2. And to find the net force, I think you can remember from your high school study that we can find this by the parallelogram method or by the calculation method. So by drawing x and y axes, I will draw the following axes, and then we can find the x and y components of each force. So for F1, for example, the x component will be F1 cosine this angle here. Now, how much is this angle? So we have drawn an x-axis, and we are looking for the angle that F1 makes with this x-axis, and we know that the roof is making an angle with the horizontal equal to 30. If this angle here is 30, then this will be also 30, and then the angle that F1 will make with the horizontal will be 90 minus 30, which is 60. So this is just a little bit of geometry. So the angle here is 60, and then the x component of the force is going to be F1, the force itself, times cosine 60, while the y component will be F1 sine 60. If we look for the force F2, it will be minus F2 cosine 60 because F2 is in the negative direction, so its x component will be in the negative part of the x-axis. And if we look for the y components for F2, it's also F2 sine 60. It's also positive because you can see that the y component is in the positive part of the y-axis. Now, if we think about finding the resultant, all we have to do is find f net along x, and this will be f1x plus f2x. So this is f1 cosine 60 plus f2, actually this is a minus because we said that the x component of f2 will be negative. And then let's look at the two forces. We said F1 will be the pressure times the area. Now the pressure is the same everywhere because we have the same drop in atmospheric pressure everywhere. And the areas are the same because the two surfaces, basically they have the same dimensions, a length of 14.5 meters and a width of 4.21 meters. So the areas and the pressures are the same, and basically then F1 and F2 will have the same magnitudes. So this will be P times A cosine 60, and this will be P times A cosine 60 as well. And then the net force along the x-axis will end up to be of a value of 0 newtons. And this makes sense because if you look at the figure here, F1x is pointing to the right, while F2x is pointing to the left, and obviously they would cancel out, so it's expected that the net force will have no x component. If we look, however, at the net force along y, this will be F1y plus F2y, which is F1 sine 60 plus F2 sine 60, which is PA sine 60 plus PA sine 60. So this is 2PA sine 60, and this is the value for the y component, and this is actually F net itself because we have no x components, right? So it will just be equal to the y component itself. Now all we have to do is just substitute the values, so we can calculate the area, we can write down the pressure. So we are told that the pressure outside drops by 75 millimeters of mercury. We can find this in Pascal first because we want the force in newtons, obviously. So remember that 1 Pascal is equal to 7.5 times 10 power minus 3 millimeters Hg. So if the pressure inside minus the pressure outside is equal to 75 millimeters Hg, then this is going to be 75 over 7.5 times 10 power minus 3, and this gives us the value in Pascal. And we can see that this gives us a value of, let's see, 10 power 4 Pascal. So we know the values of the pressure change now, and we can just substitute this here. So this would be 2 times 10,000 times the area, which is length times width. The length is 14.5, the width is 4.21, and we have sine 60 here. And the answer is going to be 1.06 times 10 power 6 newtons. This is the value of the net force, and it's obviously directed vertically up because it only has a y component.